So now we will study standard single purpose processor peripherals. These are on the slides. I will deliver these slides to you, so you can refer to these slides. And now I am going to explain each of these slides. So now this is the second slide. An introduction. What a single purpose processor performs. A single purpose processor performs specific computation task. What are examples of a single purpose processor? For example, the processors that are used in a toothbrush. They are very small microcontrollers. We can call them as microcontroller. They are very small microcontroller, and they are only performing a very specific computation task. For instance, the microcontroller that are used in the toothbrush, or the microcontrollers that are used in AC systems. These microcontrollers are only dedicated to control the temperature of the air conditioning system or an inverter. So these are air conditioning system or an inverter system. So now we can have a custom single processor that are designed for a unique task. That perform unique tasks. So it's the same thing. And we can also have standard single purpose processors. And standard single purpose processor, they are off the shelf pre-designed for common tasks. They are also called as peripherals, and we can connect these peripherals to the microcontroller or microprocessors. They are also called as peripherals, and we can connect these peripherals to the microcontrollers. These peripherals include input devices, for instance, keypad. These include output devices, for instance, LCD. We will also study different form of serial communication or universal asynchronous receiver transmitter in the upcoming slide. And we will also study some different types of analog to digital conversion. Now we will study timers. What are timers? Timers measures timed output events. For example, hold traffic light for 10 seconds, for instance. It can also be used to measure input events. So timer measures time output events. For instance, it can help us to determine that if we want to hold a traffic light for 10 seconds, so for this purpose we will use timers. Similarly, timers are also used in microwave ovens. For instance, in a microwave oven, you have these knobs, and you can cook the food or warm up the food for some specific time duration, like for instance 1 minute, 30 seconds or 1.5 minutes and so forth, so on. So for these purposes timers are used, and they are used to measure different output events. They can also be used to measure different input events. For instance, let's assume that we have installed two sensors, one is transmitter and one is receiver, and we want to count the number of people that passes through this line. So for this purpose timers can also be used. For instance, one person passes, so it means it will register that event. If the second person passes, the timer will be incremented. If the third person passes, the third timer will be incremented, and the total count will be 3. So timers are used to measure time output events. And timer are based on counting clock pulses. So let us assume that we have a clock of 10 nanosecond duration. So the clock will look like this. So this is the rising edge of the clock, and again the rising edge of the clock, the rising edge of the clock, this is the falling edge, it's the rising edge. It means that the interval from one rising edge to the another rising edge is referred to as clock duration, and let's assume that this clock duration is 10 nanosecond. So the timer can also be used to count the number of clock cycles. So this is clock cycle 1. So let's assume this is time. So it means that we have clock cycle 1, clock cycle 2, clock cycle 3. So the duration here will be, so if this is the timeline, and we start the time from here, from here, and it finishes here. So now the duration will be 10 nanosecond. For 2 clock cycles, the duration will be 20 nanosecond, and for 3 clock cycles, the duration will be 30 nanosecond. And we assume that one clock duration is 10 nanosecond. So now let's assume that we have an 8-bit counter. So the input to this counter will be a clock signal, and reset. Reset will initialize the counter to a value of 0, and it will have an 8-bit count. 8-bit count. So an 8-bit counter will count from, so 8-bit counter will count from 0 to 255. If we have a 16-bit counter, a 16-bit counter will count from 0 to 65,535. And generally speaking, an n-bit counter will count from 0 to 2 raised to power n minus 1. So if we put 8 here, so it will be 0 to 2 raised to power 8 minus 1, it will be equal to 255, and similarly 2 raised to power 16 minus 1 is equal to 65,535. So now let's assume that because this counter count the clock pulses, if the duration of the clock is 10 nanosecond, so it can count from 0 to 255. So this is the minimum count. And now this is maximum count. So the minimum count will be 0 nanosecond, and the maximum count will be 255 multiplied by 10 nanosecond. So it is equal to 2550 nanosecond, and it is equal to 2.55 microsecond. So if you are using an 8-bit counter and a clock period of 10 nanosecond, it can count from minimum to 0 second and maximum 2.55 microsecond. So if you are using a 16-bit counter, so the minimum count is 0, that is 0 nanosecond, and the maximum count is 65,535 multiplied by 10 nanosecond, assuming that the clock period is 10 nanosecond. So now this is equivalent to 655,350 nanosecond. 1, 2, 3, 4, 5, 6. So this is equivalent to 0.655 microsecond. Uh, 0.655 millisecond, sorry, it will be a millisecond. So it will be 655.350 microsecond and 0.655 millisecond. So now what is the behavior of a counter? So now let's assume that the counter is an 8-bit counter. It will count from 0 to 255. When it reaches the maximum value, it will be again reset to 0, and then it will again count from 0 to 255, and again it will reset from 0 to 255. So now we will study another type of counters that count pulses instead of clock cycles. How it will look like? So let's assume that we have a 16-bit counter. Reset will be used to initialize the count unknown value. The output will be 16-bit, that is count. It will be 15-0. And then it will count up to 2. So there are mode. So we will also set the mode for this counter. So it can count. So we are using 2 into 1 multiplexer. 2 into 1 multiplexer. So if you are using 2 into 1 multiplexer, it will look like this. 2 into 1 multiplexer. So it will have a select line. So the mode can either be 0 or 1. So if the mode we store 0, it means that it will count the clock pulses, and if it is 1, it will count the count in. So it will count the pulses. So as we know that the clock is a continuous signal, it's a continuously high and low signal. Continuous high and low signal. So if the mode is 0, it means it is counting the clock. So for this, let's assume that at this point the counter is reset, so the value will be 0. At this point, the count value will be 1 because it is counting the clock. At this point, the count will be 2, and at this point, the count will be 3. At this point, the count will be 4 and so forth, so on. If you change the mode to 1, so it means instead of counting the clock signal, it is counting pulses. So what's an example of pulses? So now we can have some kind of pulse. So the pulses will look like this. So now this is some pulses. This is count in. So it's pulses. So this is pulse 1. This is pulse 2. This is pulse 3. And this is pulse 4. Actually, these pulses are generated at non-regular interval. So at this point, let's assume that the count is reset here. The count will now at this point will be 1. The count at this point will be 2. The count at this point will be 3. And the count at this point will be 4. So when it is generating pulses, so these are actually count A, and count A is actually pulses, and these pulses are generated at non-regular interval. These pulses may indicate some events, and what can be examples of these events? These events can be, let's assume that if a person is passing, let's assume that if this is a transmitter and a receiver, and if I passes through this way, a pulse will be generated, one pulse will be generated. Again, if another person passes, so this is person A passes, so it will generate a pulse. Another person passes through this way, person B passes, it will generate a pulse, and person 3 passes, it generates. If no person is passing through this way, no pulse will be generated. So this counter clock, if you are counting the clock, so clock or the signal that is generated at regular interval. Is this pulse is generated at this point, at this point, at this point, and at this point. Okay, so now we will study interval timer, and this interval timer indicates when desired time interval has passed and we set terminal count to desired interval. I will now explain this a little bit. So now let's assume that we are using a 16-bit counter. So it will count the clock signal, and this reset will be used to initialize the count to 0. So after reset it will be initialized to 0, and the output 16-bit value will give a value from 0 to 65,535. So let's assume that the clock period The clock period is